Hey, so let's take a look at the practice problems for Unit 7.2, Lesson 5 in Desmos today. So let's begin with the warm-up. It says, here are the second and fourth figures in a pattern. Draw figures 1 and 3. So I'm looking at these figures, and I have to decide a pattern that will allow me to figure out what figure 1 must have been and what figure 3 would be. And I look at figure 2, and I notice that you could sort of cut it in half right here. If you think of this like orange side, I don't know why I said orange, it was green. It's green side and this purple side. They're the same, right? Except they're just flipped, or if you want to be a little more mathematical, you would say they're reflected, where this has 2 large gray boxes on top and then 3 small white on the bottom, and this has 2 large gray on the bottom and 3 small white on the top. And so it looks like figure 4 has 4 of these sections, right? This has 1, 2. Figure 4 has 1, 2, 3, 4, and they alternate from the gray boxes being on top and then bottom, then top, then bottom. So I think what the pattern here is that one of these gray, why can't I say green? One of these green sections gets added on to each new figure. So, but each time it gets flipped. So let's see here. It looks like in figure 2 and 4, the gray boxes are on the top both times. That could mean that it's supposed to be gray on bottom for the odd ones and it flips back and forth. It could also mean that the gray ones are always on top in the first section and then the rest of the sections are being added on after that. I actually don't think there's really any way to tell. So I think I'm going to go with the second way. I think I would draw it as having the 2 shaded in sections on the top and the 3 non-shaded in sections on the bottom. And then for figure 3, I'm going to make 3 of these sections. So 1, 2, 3. And then I'll start with the 2 shaded sections on top, then 2 shaded sections on bottom, and then 2 shaded sections on top again. And I got to put my 3 non-shaded sections in the rest. I think that's how it's supposed to be. I don't know. Maybe you have a different answer that also makes sense. I don't know. All right. So next we're actually into the practice part, and it says, a performer expects to sell 5,000 tickets for an upcoming concert. They plan to make a total of $311,000 in sales from these tickets. Okay, so assume that all tickets have the same price. What is the price for one ticket? All right, so what we're trying to calculate here is what we refer to as a unit rate. Or in this case, if we wanted to be even more specific, we could call it a unit price, just because the type of rate we happen to be working with here is a price. It's a dollars per something, dollars per ticket. Okay, in math, unit just means one, or even just in the real world, when you talk about, I need this many units of something, well, each unit counts as one. So when you say unit rate, you're talking about how much does it cost for one, or how much of this can I get for one. All right, so we want the price for one ticket. So we can call that the price per ticket. And we can write that using units and symbols as dollars per ticket, right? Dollars, and then the slash kind of means ticket, or sorry, kind of means per, and then the T stands for ticket. Sorry, that's a really bad T right there. All right, well, this actually kind of tells you how to solve the question too. Dollars per ticket also kind of looks like a fraction with the dollars on top and tickets on bottom. And that's exactly what we're going to do to solve this question. I'm going to take the number of dollars given from the question here, 311,000, and divide it by the number of tickets, this 5,000 right here. And that will give me my unit price, the number of dollars for one ticket. So let's see here. You can use a calculator for this one. These are some big numbers. I mean, really, the zeros are just going to cancel each other out, right? So the answer to this is going to be the same as the answer to just 311 divided by 5. And I know that 5 goes into 100 20 times. So 300, it's going to go in 60 times. And then into that 11, 2 more times, and some decimal. It should wind up being 62 point something. I don't know. Let's figure it out. So I'm going to do 311,000 divided by 5,000. $62.2, but that's not how humans speak. We would add that extra zero on the end for cents. And so this is $62.20, not $62.02. $62.20 in dollars per ticket. I guess you could put the dollar sign in the front too, but I don't know, I wanted to put this whole dollars per ticket thing at the end. There's multiple correct ways of writing that. All right, so now how much money will they make if they sell 7,000 tickets? Well, we know that each one cost $62.20, right? So if we need to know how much money 7,000 tickets is going to cost, well, we should be able to just multiply $62.20 times, this dot means multiplication, 7,000. And we should figure out how much that's going to cost. So let's see here, $62.20. I didn't have to put that last zero, but I felt like it. Times 7,000. 7,000 tickets equals $435,000 and $435,400, which that makes sense to me because in the original problem, they said they were going to sell 5,000 and they were going to make $311,000. Now we're making significantly more, or we're selling significantly more, 7,000. And so the amount of money is significantly more. It's more than 311,000. So I feel like our answer makes sense. $435,400. Okay. And so now 1.3 is asking us, let me adjust this a little bit. To write an equation to represent the relationship between the number of tickets sold, which we'll call X. I was labeling tickets as T up there, but okay, so X is going to be tickets. And the total amount of money in dollars that they make will be Y. Okay, so Y is going to stand for the dollars. And we need to make an equation here that explains how you could calculate the number of dollars needed to purchase any number of tickets. Well, let me write this out in words real quick. I know that the cost of any number of tickets, if you're doing this on Desmos, you can't write this stuff, right? Like I'm just writing this to kind of help you understand what I'm doing, but I think in Desmos you probably just want to enter the equation that we're going to come up with. The cost of any number of tickets equals the price times the number of tickets. Right, this is a word sentence that says what we're trying to do here. The cost of any number of tickets, which is going to be the dollars, y, so that's why I kind of put it in purple to match with that, equals, so that's where we're going to use an equal sign in our equation, the price times the number of tickets. So the number of tickets is represented by x. Maybe I could have used a different color for the price, but I only have 3 colored markers, so we only can do what we can do. So let's put this together now. Cost of any number of tickets, that's represented by a y, equals, okay, I just literally need an equal sign there. The price, well, the price for one ticket, we calculated that in an earlier question. It's this $62.20 right here. So I'm gonna kind of, $62.20 times the number of tickets, which we're being asked to represent with just the letter x. There's our equation. Y equals 6220x. And so with all of these equations that represent proportional relationships, this is a proportional relationship between how many tickets you buy and how much money you're gonna have to pay, right? They always boil down to y equals your unit rate or constant of proportionality times x. We have a general form of that. When I say general form, I mean a form that works in general. And we write it as y equals kx. And so really all we did is we wrote this here, but we found our k, which was $62.20, right? I called it the unit rate, but unit rate and constant of proportionality are the same thing. And so once we found this k, we just plugged it into here. We wrote y equals 6220x instead of y equals kx. This works regardless of what these letters are. Like I'm saying y equals kx, but it could be d equals kt or g equals km, right? The only one that I'm always saying the same letter is k, because k represents your constant of proportionality. But instead of y and x, you could have q and b or a and l. It doesn't really matter. All right. So here it says, if they make $379,420, how many tickets will they have sold? So the first thing I notice is that the value that they've given us is an amount of money. That is represented by y in my equation, right? Y was dollars. They've given me a number of dollars. So I can make a substitution here by putting this number that they've given me where that letter goes in the equation. So I can rewrite it as 379,420 equals 6220, $62.20, times some number that we don't know. This times some number we don't know has to equal that. So lots of times in class, I like to write this way, 6220 times blank equals 379,420. And we've done enough of these at this point that you should see, oh, if I need to fill this blank with a multiplication, I just work backwards using division. This times blank equals that tells me that I should do this divided by this in order to fill that blank. So let's do that. Let's do 379,420 divided by $62.20. Grab the old handy dandy. I can do some of this math in my head, but I don't know if I can do 379,420 divided by 6220. That's a lot. 379,420 divided by 6220 equals, oh, I was off the screen that whole time. My bad. 6,100. So they will have sold 6,100 tickets if they make $379,420. Okay. And then lastly, it asks, how many tickets will they have to sell to make $5 million? Well, I look at the fact that they're giving me an amount of money again, right? This question is literally the exact same as the previous question, just worded differently. The first question said, if they make this much money, how many tickets did they sell? The next question is asking me, how many tickets do I have to sell to make this much money? They're worded differently, but they're the exact same thing. I'm going to do the exact same thing I just did previously. I'm going to take this amount of money and I'm going to put it where y goes in this equation, because y represents dollars. This is called making a substitution. I'm substituting a known number for a variable that represents it normally in an equation. 5 million equals $62.20 times some unknown number of tickets. And so we just use the exact same process we used last time. If I need to know that this times this unknown number equals 5 million, I work backwards using division. I'm going to do 5 million divided by 6220 and see how many tickets that is. So let me just draw a little arrow. I'll do this over here. 5 million divided by 6220. We better get an answer that's a lot bigger than the last question. The last question, they only made 379,000. This time they're making 5 million. That's over 10 times as many tickets. It's like 15 times as many tickets. So our answer is going to be like 15 times bigger than this 6,000. So it's going to be somewhere in the neighborhood of like 80,000, 90,000, somewhere around there. It's a good habit to get into, like thinking about what your answer should be before you do it. 5 million divided by 6220. $80,385. No, tickets. This isn't dollars. I'm mixing myself up. This is number of tickets. 80,385.8521. That makes me wonder if I messed up. Like, it doesn't feel right to get a decimal answer when the question's about tickets. I can't sell 0.85 of a ticket, right? Like, how do you sell 80,384, 80,385 tickets and the next person buys 0.8521 of a ticket? Like, that doesn't make sense. So two things are happening here, or one of two things. Either A, I messed up, which I'm going to check real quick, it's possible, or B, the question is asking how many tickets they need to sell to make at least $5 million. And then I need to round this number up, because if they only sold 80,385 tickets, they'd be just under $5 million. So they need to sell 80,386 tickets to get just over $5 million, right? Because you can't sell 0.85 of a ticket. So let me just double check what I did here. They said $5 million, yeah. I did 5 million divided by 6220. That all seems right. I'm going to punch the numbers in one more time just to. Same thing. All right, so I'm confident in my answer. So I think our answer needs to be 80,386 tickets. Because if they would need to sell this many tickets to get exactly 5 million, well, they can't sell exactly this many tickets. It doesn't make sense logically in the real world. So we got to bump up, we got to round up to that next one to get at least $5 million. I'm going to write the word tickets here. All right, let's look at the next part. It says, here's a polygon on a grid. And this is a polygon. A polygon is just a shape with multiple sides. All right, so draw a scaled copy of the polygon using a scale factor of 3. All right, so first thing I want to do is count boxes here, so I know how big this thing is. This is 2, 2, 2. This kind of goes across 2 boxes diagonally, and this kind of goes across 2 boxes diagonally. So this thing's 2 all the way across. if I'm going to use a scale factor of 3, that's not too bad. 2 times 3 equals 6. This is my scale factor here. So I just need to make sure that when I draw this thing, it comes out 6, 6, 6, and then the diagonal parts go through 6 boxes. I should probably do it. I got to make sure that wherever I work, I have 6 boxes worth of space. So let's see here. I'm going to start right here. That way I know I have plenty of space. So if I start here, I don't count that box. That's a mistake I see students make. Sometimes they'll go 1, 2, but you really actually only gone 1 box. So if I'm going to start here, 1, 2, 3, 4, 5, 6. Okay, so there's one side. And then starting here, 1, 2, 3, 4, 5, 6. All right, so then I should go to the same spot down here. Let me draw these sides. Now, I know that if you look at this spot on this drawing, it goes out 2 boxes to the point here from, this is the vertical center of these 2 points. So let me find the vertical center of these 2 points between here and here. 1, 2, 3. And then since from this center point here to this vertex is 2 boxes, if I'm using a scale factor of 3, in my scale drawing, it needs to be 6 boxes. So 1, 2, 3, 4, 5, 6. Let me grab a straight edge for these lines. There we go. And so it told me to label the copy A. So I'll call this shape A. And it has 6 here, 6 here, 6 here, etc. Now it says, draw a scaled copy of the polygon with a scale factor of 1/2 and label it B. Okay, this should be kind of easy because I'm going to take all of these measurements and just multiply them by 1/2. So that just means to figure out half of the numbers, and half of 2 is 1. So I'm just going to draw it again, but everything that used to be 2 is now 1. So 1, 1, 1. This last part's a little weird because when I try to find the center point between here and here, I kind of have to eyeball it in the middle of this box. And then instead of going out 2 boxes from there, I'm going to go out 1. So that part's a little different because the vertex of the shape is like in the middle of a box. That's okay. And it told me to label that B. Is polygon A a scaled copy of polygon B? Absolutely. It's a scaled copy if I can find a scale factor, right? So let me label this 1, 1, 1. Well, I see that I can take any side of B, multiply it by 6, and get the sides of A. So they're scale copies of each other. Just the scale factor to go from B to A is 6. Oh, and that's exactly what they're asking here. So the scale factor to go from B to A is 6. All right, let's look at the explore part. It says, a cheetah ran 100 meters in 6 seconds. A sloth took 15 seconds to move 1 meter. A mosquito flew about 5 meters every 9 seconds. And Usain Bolt ran 6.5 meters per second when he broke the 100-meter dash world record. Okay, so we're supposed to complete this table with 2 different ratios for each animal or person that it spoke about. One ratio is speed. That's calculated as meters per second. Take the number of meters that something traveled, divide it by how much time that took, and that's a measure of its speed. So like miles per hour, meters per second, feet per second, stuff like that. The other one is if you were to do the division the other way. If you were to take the amount of time they took, in this case seconds, and divide that by the distance that they traveled. This is how we talk about pace. Like when we do, like when you run a mile, like in PE class, you don't usually tell your friends, oh yeah, I ran the mile today and I did it at a 5.2 miles per hour, like that was my speed. We don't do that. We talk about our pace. We say, oh, I ran a 7-minute mile or an 8-minute mile. What you're saying is it took you such and such time per 1 mile, right? So when you say the time per distance, that's pace. So they want us to do this both for all 4 of these animals or people, speed and pace. So let's see here. The cheetah ran 100 meters in 6 seconds. So that's 100 meters divided by 6 seconds. So 100 divided by 6, I'm pretty sure that's 16 2/3. 16 2/3 meters per second. Every 1 second, this cheetah is covering 16 meters. That's like half of a football field. No, not even close. It's like, it's like a fifth of a football field, because a football field is 100 yards. So a fifth would be 20 yards, but meters are a little bit bigger than yards. So 16 2/3 meters, probably close to about 20 yards. Every second though, it's fast. All right, so the pace, on the other hand, would be if we just flip the division. Instead of doing meters divided by second, we're gonna do seconds divided by meters. So 6 seconds divided by 100 meters. Well, I know that when I divide something by 100, I'm just gonna take the decimal place of the dividend, the thing I'm dividing, and move it over 2 spaces, right? Because there's 2 zeros in this number. So this is 0.006 seconds per meter. So what this is saying is that it only takes, man, that doesn't seem right. Yep, I messed it up. It's really good to be able to look at your answers or look what you're doing in math, and like if it doesn't feel like it makes sense, stop and think about it for a second. 0.006 seconds per meter would be so fast. I realized that when I moved the decimal point over, the decimal point in the number 6 is right here. If you move it 2 spaces, 1, 2, you create 1 empty space, and so it should have been 0.06, not 0.006. 0.06 seconds per meter. That's still really fast though, right? So what that's saying is that it takes the cheetah 0.06 of 1 singular second to travel each meter. All right, the next one for the sloth. Sloth took 15 seconds to move 1 meter. Okay, so 1 meter divided by 15 seconds. No, let's just write it as a fraction, make our lives easier. This is 1/15 meters per second. So every 1 second, this sloth is only moving 1/15 of a meter. Ugh. It's like a few inches, I think. Okay, and then the other way, the pace is 15 seconds divided by 1 meter. So it's just 15 seconds per meter. It takes the sloth 15 seconds to go every meter. That's pretty clear from the information we were given. All right, next for the mosquito. 5 meters every 9 seconds. So let's do 5 meters divided by 9 seconds. That's 5/9, right? We could just write it as 5/9. Let's write it as a decimal just for fun. I'm pretty sure it comes out to 0.5 repeating. I think 5/9 is the same as 0.5 repeating. Let's see. 5 divided by 9. Yep. Don't worry about that 6 at the end. That's just the calculator doing calculator stuff. So 0.5 repeating meters per second. So that's a little over half a second. Or I mean, a little over half a meter is what I mean to say. Every 1 second, the mosquito goes a little over half a meter. And then if we do it the other way, 9 seconds for every 5 meters. Okay, so it's 9/5, right? 9/5, 9/5. 9 divided by 5, 1.8. So 1.8 seconds per meter. It takes the mosquito about 1.8 seconds every time it travels a singular meter. All right, and lastly, for Usain Bolt, it says that he went 6.5 meters per second. Okay, so they're actually giving us this one right here, right? It's literally in the information. 6.5 meters per second means 6.5 meters every second. They gave us that part. Now we have to figure out the pace. How many seconds per meter is that? Okay, well, we know that this is equal to 6.5 meters for every 1 second, right? I'm just rewriting this in a different way. Well, to find the seconds per meter, we literally just flip it, right? Now we want seconds on top and meters on bottom. So this is 1 second for every 6.5 meters. Well, let's see what 1 divided by 6.5 is. 1 divided by 6.5. 0.538, blah, 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 whatever. We'll just call it 0.15. 0.15 seconds per meter. So as he's running about every 0.15 seconds, he's covering a meter on the ground. Super fast. All right. Thanks for watching. That's it. See you next time.